Let's talk about vertex edge graphs and adjacency matrices. And an adjacency matrix is a way of showing connections between coordinates on a vertex edge graph. So here are two vertex edge graphs. Just want to point out some of the obvious things that you, I'm sure, have already noticed. This one has arrows and this one does not, which means that in this particular case, as a small graph too, I can go from A to B and B to A, but in this case, I can go from A to B, but not B to A. And that's going to be demonstrated in our vertex edge graph. So in a vertex edge graph, we're going to have, well, all our vertices. Vertices are the dots, the little, some people call them nodes, N-O-D-E-S. So A, B, C, D, E. Here we go. And this is a review because, of course, you've seen this before. A, B, C, D, E. A, B, C, D, E. There we go. And I'm just going to figure out where I'm coming from and where I'm going to. So where I can go from and where I can go to. So this is from and this is to. So can I go from A to A? And that sounds ridiculous, and we've been through this, but the answer actually is no. I mean, you might be like, well, I'm already there, so I could put a 1. 1 means there's one way to get there. But when you're at A, there's not a way to get to A. You're already there. There's not a path to A is what I'm saying. Not an edge that leads there. But there is an edge that goes from A to B. There is not an edge that goes from A to C. There is one edge from A to D. There are 0 edges from A to E. Basically, we're putting the number of edges that lead from one place to the other. And you haven't seen this much, but there could be 2 roads that go from A to B. So you could have a couple options there, right? Okay, can I go from B to A? Well, absolutely. Can I go from B to B? No. Can I go from B to C? No. Can I go from B to D? Yes. Can I go from B to E? No. You got this, all right? This is going to be super easy. We're going to start going really fast. The only place I can go from C is E, so we'll do that. We'll fill in everything else with a 0. The only places, there are 3, that I can go from D are A, B, and E. So A, B, and E. Everything else is a 0. And from E, the only places I can go are C and D. So those 2. Everything else is a 0. That was pretty straightforward. Here goes. Let's do the next one. Now the next one is different because it is directed. So again, I can go from A to B, but not B to A. So I have to be cognizant of that. Let me point out a little bit of symmetry that's happening over here. If I read a row, it's the same as the corresponding column in a non-directed graph. So here goes. I'm going to read the A row. 0, 1, 0, 1, 0. If I read the A column, it's 0, 1, 0, 1, 0. Not a coincidence, okay? That's not going to happen over here because it's directed. A goes to B and C. A goes to B and C. Everything else is a 0. B goes to C and E. Everything else is a 0. You can see where this is going. And I say B goes to C and E. What I really mean is there is one path from B to C, one path from B to E, and that's why we put a 1 there, okay? If it'd be 2 rows or 3 rows, 2 paths or 3 paths, we'd do that instead. C goes to D and only D. Everything else is a 0. D goes to E. Everything else is a 0. E goes, well, nowhere. If you ever get to E, you're stuck. Sorry, you can't get out. So E doesn't go to A, B, C, D, or even to itself. There we go. So we have gone from a vertex edge graph to a matrix. Now we're going to go back the other way and go from a matrix to a vertex edge graph. So sketch the vertex edge graph that corresponds to each adjacent matrix and state the degree of each vertex. This is going to be interesting. The second adjacency matrix represents a directed graph. All right, so we're going to use arrows on this one, not this one. This one's the second one. It represents the directed graph. So A, B, C, D. All right. From A, I cannot go to A. From A, I can go to B. From A, I can go to C. From A, I can go to D. All right, there we go. We got that taken care of. Let's keep going. From B, I can go to A. That's done. From B, I can go to C. From B, I can go to D. From C, I can go to A. From C, I can go to B. From C, I can't go to C. I can't go to D. And actually, we're done at this point because everything is taken care of. But we'll just read through it anyway. D goes to A. D goes to B. And that one's finished. All right, they also said state the degree of each vertex. I'm going to do that in red just for fun. The degree of A is 3. I'm saying A equals 3 as if it was a variable. It's not, but the degree of A is 3. B has a degree of 3, C has a degree of 2, and D has a degree of 2 for slightly obvious reasons. So like D has 2 edges coming out of it. All right, here goes. This one's going to be directed, and it has 5 vertices, A, B, C, D, and E. All right, let's use arrows. A goes to itself. Interesting. Okay, arrow from A to A. A goes nowhere else. All right, B goes to A with an arrow. B goes to C. B goes nowhere else. All right, I'm looking there. C goes to itself. C goes to D. And it goes nowhere else. D goes to B. D goes to C. Oh, D goes to C. Let's just double arrow that thing. And that looks like an if and only if. That's a math joke. And D goes to itself. And D goes to E. Man, you can go almost anywhere from D. Can't go to A, though. That looks like a G. It's actually an arrow from D to itself. All right. E goes to itself. No, it doesn't. E goes to A. E goes to B. E goes to D. Let's double arrow that, and that's it. All right. The degree. All right, for this one we're going to count the number of arrows that are coming out of each vertex. So A, B, C, D, E. A has 1 arrow coming out of it, okay? And actually, let me give you another way of doing it. You could total these up. So A is 1, B is 1, 2. There you go. See, notice how I'm using the row for that, but I also see it here. B has 2 arrows coming out of it. C has 1, 2, so 1, and then this one, doesn't look like it, but this one, because it goes towards D as well. And it comes from D also. D has 1, 2, 3, 4, which you could count on here. 1, 2, 3, and 4. And E has 1, 2, 3. All right, let's proceed. We are going to deal with adjacency matrices in the most practical way possible. We have a small bus line. We offer service to several points in Greensboro, and there's a High Point Road, East Wendover, West Wendover, Battleground, North Elm, South Elm. It's going to be fun. Let's keep going. This is going to be directed. Draw the directed vertex edge graph and write the adjacency matrix. We'll call the adjacency matrix A. We're going to find A squared and A to the third and then answer some questions. This one's going to be very involved, so hunker down. Here we go. We're going to have a bus hub at High Point Road. We're going to have one at East Wendover. We're going to have one at West Wendover. We're going to have one at Battleground. We're going to have one at North Elm, and we're going to have one at South Elm, and I probably didn't leave enough space for this, but that is okay. We're going to deal with it. All right, reading through these bullet points, I'm going to read quickly. Follow along. High Point Road bus delivers to East Wendover and South Elm. So High Point goes to East Wendover and goes to South Elm. East Wendover bus delivers to West Wendover. East Wendover goes to West Wendover. The West Wendover bus, notice I'm using arrows because they said directed, by the way. The West Wendover bus delivers to Battleground, North Elm, and to High Point Road. Okay, things are starting to get cluttered, but we'll deal with it. Battleground delivers to West Wendover. Battleground goes to West Wendover. They're going back and forth. North Elm goes to East Wendover. North Elm goes to East Wendover. It's okay that they cross in the middle. It's fine. That intersection means nothing important. East Wendover and also goes to South Elm. And South Elm delivers to Battleground. South Elm delivers to Battleground. Just so I don't clutter up the inside of that, I'm going to bring this one around. That is not an indication of the actual route the bus takes. Okay, we are going to make an adjacency matrix. We're going to call it A. And I'm doing that for when I type it into desmos.com/matrix. Now, on this video, I am not using desmos.com/matrix. I'm actually going to use a calculator. But that's okay. So I'm going to have High Point Road. Oops, HB. High Point Road. High Point Road. I'm sorry. High Point Road East Wendover, West Wendover, Battleground, North Elm, and South Elm. And everything I just said I have to put over here too. High Point Road, East Wendover, West Wendover, Battleground, North Elm, South Elm. Okay, I have not left much room for the other things that they asked for. And that's okay. We'll deal with it because I'm going to show you what's on my calculator and we'll walk through it. Now, if you want to grab a separate piece of paper for what's about to come, feel free, but I didn't leave you much space here. I was trying to save my own paper and then now I'm wasting yours. I apologize. Okay. We're going to fill in this directed vertex edge graph. And just to make things a little bit easier to look at, I'm going to do this. Otherwise, these numbers are all going to run together and things are going to get sloppy and messy. And we're going to have zeros and ones everywhere and not know where anything really belongs. And it will be tragic and sad. There we go. Yeah, we'll put one up at the top too. Okay. So here goes. High Point Road doesn't go to High Point Road. East Wendover doesn't go to itself. West Wendover doesn't go to it. Like, why would you ride a bus back to where you already were? So I'm just going to go through here and do something obvious. And just to make this stand out, I'm going to put it in red. So 0, 0, 0, 0, 0, 0. This is any bus route to itself. South Elm to South Elm. North Elm to North Elm. Battleground to Battleground. You get it. Okay. High Point goes to East Wendover and South Elm. East Wendover and South Elm. I'm going to go through and put in zeros at the end. East Wendover goes West Wendover, and that is it. And you could get this information from your vertex edge graph. You could get it from up here also. East Wendover goes to West Wendover. West Wendover goes to Battleground, North Elm, and High Point. Battleground, North Elm, High Point. Battleground goes to West Wendover. I'm going real fast. North Elm goes to East Wendover and South Elm. South Elm goes to Battleground. Okay. You can, again, verify it with what you have written or your vertex edge graph. I'm having a hard time saying that, apparently. Okay. So I'm going to put zeros everywhere that I don't have a number. And, oops, that one has an awkward little apostrophe backwards in front of it. I'm sorry. That's going to bug you, isn't it? It's bugging me. I'm going to get the white out. Cover it up. Pretend like it never happened. There we go. Okay. All right. I would love to type that into desmos.com/matrix. I'm actually not. I'm going to show you something I haven't really shown you before, but I'm going to do it anyway because I'm going to use a calculator just in case you really want to. But you can use this, type it in as matrix A in desmos.com/matrix, but I'm going to press second and matrix. And I want to edit matrix A, and it is going to be a 6 by 6 matrix. And I'm just going to type these numbers in. I'm going to go really, really fast because I don't want to waste your time. 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1. I messed up. So now we start all over and you're stuck watching me as I type this whole thing over again. So I'm going to go down this time. 0, 0, 1, 0, 0, 0. All right. Let's do it this way. Sorry to waste your time. Feel free to skip this part of the video. Or you could take this opportunity to type it in yourself into a calculator or to, well, desmos.com/matrix. I used to work at a bank, and I basically would just sit and type numbers all day. So I got really fast at that kind of thing. Got a little cocky in my skills right there. Okay, if you want to pull up this matrix, if you're using the calculator, second and matrix, there's the button right there, by the way. And where it says names, I'm just going to press enter, and there it is. Beautiful, isn't it? I'm going to quickly double check it and make sure I'm right, because if I'm wrong, then it screws up everything, and then the whole problem falls apart. All this work is for nothing, and we'll all cry ourselves to sleep. Okay, they also said find a squared and a to the third, and I do not have room to write that. So I'm going to grab a scrap piece of paper and write it, and you can as well. second. Should have given you more space. And this is going to be a little bit time consuming. I apologize for that, but it is going to be necessary because it's going to help me explain things a whole lot better. So here goes. I want to square this matrix and I want to cube this matrix also. So here we go. Second and matrix and A, and I want to square it. And that's what I get. And I want to write that down. And so this is a continuation of what would go in the space if I would write smaller or give you enough space. So A squared is this. By the way, this is A. So A squared is 0, 0, 1, 1, 0, 0, 1, 0, 0, 1. Now this might be super boring watching me write this. I get it. But I'm doing this so I can use this as a reference as we answer some of the other problems. There we go. And I'm also going to cube matrix A, and we'll do that as well. So I'm going to cube it. So let's see, second matrix and A, and then we're going to raise it to the third power. There it is. Okay, 1, 0, 1. Again, I know this is super boring. Watching me write numbers while talking in the most monotone voice ever. But I hope you understand what, sorry, I can't do it. I hope you understand what this represents though. And that's important to know what this represents. This is going to represent, this matrix is going to represent the number of ways you can get from, for example, High Point Road to High Point Road in 3 bus rides. And the answer is 1. There is 1 way to get from High Point to High Point Road in 3 bus rides. Notice the numbers I'm pointing at. So this is EW, WW, Battleground, North Elm, South Elm, and we have U, ooh, buh, ne, se. There we go. We have the same thing up here. High Point Road. If you're not writing all of this, that is fine. That is totally fine. However, when you are trying to figure out where you got answers to the problems that are about to happen, you might be a little bit stumped. So be careful. Oops, I should say EW, West Wendover, Battleground, North Elm, South Elm. Okay, I have all those written. That took a lot of time, but it's going to help us as we get to the actual questions that are to come. Feel free to pause the video here if you need to, but I'm going to move on. How many ways can you get from West Wendover to East Wendover with exactly 2 bus rides? Okay, exactly 2 bus rides mean I have A squared. Okay, exactly 2 bus rides. List every possible path. So I want to go from west to east. Don't use this matrix. This is 1 bus ride, okay? Don't use that. We want to find with 2 bus rides. So I'm going to use A squared, and I'm also going to be looking from West Wendover to East Wendover. So from west to east, there are 2 ways to go from west to east in 2 bus rides. And again, it's important to know the numbers I'm pointing at as I say it. 2 ways to go from west to east in 2 bus rides. So there are 2 paths. And then it says list them. So now we have to figure out what they are. I'm going from west to east. I want to go from here to here. But as I go from here to here, I need to ride the bus 2 times, okay? So here's one. I just noticed it. From West Wendover to North Elm to East Wendover. So West Wendover goes to North Elm, which goes to East Wendover. We also could go West Wendover to High Point to East Wendover. West Wendover, High Point Road, East Wendover. Okay, that's one way. And now we'll go to number 2. How many ways can you get from South Elm to West Wendover with exactly 2 bus rides? So 2 bus rides, same idea. This means A is squared. I'm looking at the same matrix, and I want to go from South Elm to West Wendover. So South Elm to West Wendover. Oops, let me get you where you can see it. South Elm to West Wendover, that's 1. Just 1. There's 1 bus ride, there's 1 path, sorry. 1 path that I can take from South Elm to West Wendover that takes exactly 2 bus rides. So there is 1 path, and I want to find it going from South Elm to West Wendover, and I'm looking for it now. Let's see. Nope. Nope. Yes. Battleground to West Wendover. So I start at South Elm, I go to Battleground, and then I go to West Wendover. Okay, let's keep moving. Exactly 3 bus rides. So now I'm using A cubed. Exactly 3 bus rides using A cubed, and I'll list every possible path. So going from Battleground, East Wendover, Battleground to East Wendover. How disappointing. 0. Battleground to East Wendover. Oh, I'm looking at the wrong one. Sorry. I was looking at A squared. It's A cubed. Oops. Not starting this video over. Battleground to East Wendover. There are 2 ways of doing this. So there are 2 paths. And list every possible path. So let's list every possible path. And I'm going to start at Battleground, and I'm going to end at East Wendover, which means I ride the bus again, I ride the bus again, and then I end on East Wendover. And we're going to do this twice, okay? Because there are 2 ways of doing this. Notice I have 1, 2, 3 bus rides. So Battleground, I'm about to fill in those. We'll figure out what they are. Let's look at our vertex edge graph to do it. Again, difficult for me to say. Battleground goes to East Wendover. We're going to ride the bus 3 times. Battleground, East Wendover. 1, 2, 3. There's one of them. Okay. West, High Point, East. West, High Point Road to East. There's one of them. Let's do another one. From Battleground, I could go, West, North Elm, East Wendover. West Wendover, North Elm, East Wendover. There we go. All right, here we go. How many ways can you get from West to Battleground in 3 rides or less? So I need A cubed, and I need A squared, and I need A to the first, okay? I need 3 rides or less. I'm going to use all 3 of those. So let's total some things up. This one will take just a moment, but it won't be as bad as you think. So here goes. 3 rides. Let's start with the cubed. And I'm going from West to Battleground. So West to Battleground, there's 3. So there are 3 paths with 3 rides. Okay. Notice it didn't say to list them because it would take all day. We're not going to. And now we're going to try A squared. So we're going from West Wendover to Battleground. West Wendover to Battleground. Oh, there's 0. So I'm going to put 0 just so I'll know that I've considered it. So there are 0 paths with 2 rides. And now we look at A to the first power, going from West Wendover to Battleground. West Wendover to Battleground has 1 path. So 1 path with 1 ride. 1 bus ride. But then it said how many ways, like total, it's implied. So there are 4 total paths. We are not going to list them. There we go. Vertex edge graphs and adjacency matrices in a nutshell.